Okay, here's a picture of a hexagon, a regular hexagon. I chose arbitrarily a side length of 2, since it's a regular hexagon. All the sides have a length of 2. The problem we're trying to solve started with the fact that we drew 2 diagonals like this, and we're supposed to find the sum of the area of these 2 triangles. So we have the area of 1 plus the area of triangle 2. We're supposed to find its ratio to the area of quadrilateral 3. So this is what we want to do. Now, there's quite a bit involved in being able to do that. You have to understand that if you have a right triangle, like this, and that one of the angles is 30 degrees, and that the other is 60, that it turns out that the short leg, the sides have to be in the ratio 1 to 2 to the square root of 3, where 1 is the short leg, 2 is the hypotenuse, radical 3 is the short leg. So if you have another triangle that looks like this, 30, 60, and I tell you this is 5, the short leg, the hypotenuse is twice that, and the long leg is radical 3 times the short leg. So on a 30-60 right triangle, if you know one of the legs, you can find the other 2 legs quite easily using these ratios right here. The other thing that you have to know is that in a regular hexagon, if I draw yet another diagonal here, let's say this one, from the same vertex, I've actually created 1, 2, 3, 4 triangles, and the sum of the angles of each triangle is 180. So we have 6 minus 2, and this works for any polygon. The number of sides, take away 2, gives you the number of triangles. If you multiply that by 180, you've got the sum of all these interior angles right here. 1, 2, 3, 4, 5, 6. So 4 times 180 is 0, 32, 720. Now in a regular polygon, all these angles at each vertex are equal. So in this case, if I divide by 6, I find that each interior angle of a regular hexagon is always 120. So this angle right here is 120 degrees. And now to find the area of a triangle, one way to do that is to find its altitude, which is drop from a vertex perpendicular to the opposite side. So this angle right here is a right angle. And guess what? If this is 120 degrees, this is 60, because these 2 triangles are congruent, and this is 30. And there's the hypotenuse. Now if we were solving the problem in general, this would be an x instead of a 2. But in a 30, 60, 90 right triangle, whatever this is, whatever this hypotenuse is, this side right here is half of that. And I'm sorry, the altitude is opposite the 30, so it's 1, half the hypotenuse. And so this leg right here is radical 3. And so I can do that here too, because this is 60 and this is 30. So if I look at this big triangle, triangle number 2, it has a base of 2 radical 3. Radical 3 plus radical 3 is 2 radical 3. The area of a triangle, and I'll put a little 2 here to emphasize that we're finding the area of triangle number 2, is 1/2 the base, which is 2 radical 3, times the height, which is 1. This distance right here. I meant to write a 1 there. And half of 2 radical 3 is radical 3. Okay, and we could do the same exact thing for triangle 1 and end up that it has an area of radical 3. Now we get a slightly different answer if we label these sides with an X instead of a 2, but that can be a strategy for solving a problem. Make up a specific example and see what happens. Now, how do we find the area of region 3, the quadrilateral? Well, actually, this diagonal helps us, because now we can say that this triangle over here is, let's call it 3e sub a, and this is 3 sub b. And if this is a 30-degree angle, and this is a 90-degree angle, because the whole angle is 120, if we take away this 30, that leaves 90. So we can find the area of region 3A, or triangle 3A, by calling this a base and this distance a height. So the area of triangle 3A, 3 sub A, is 1/2 the base, which is this 2 right here, times the height, which is this distance right here, radical 3 plus radical 3, or 2 radical 3. Half of the 2 is 1, so the area of triangle 3A is 2 radical 3, and guess what? We could do the same exact thing for triangle 3 sub B. We get 2 radical 3. So the area of quadrilateral 3 is the sum of these two numbers, 4 radical 3. That's the area of quadrilateral 3. And now we're ready to substitute into the formula. Here's our formula. Add 1 plus 2 together. That's radical 3 plus radical 3. And we want its ratio to the area of quadrilateral 3, which we found to be 4 radical 3. The radical 3's cancel out, and the ratio turns out to be 1/2. That's your answer right there. Again, if we had x's in the answer instead of 2's, the strategy would be the same. It's just at the end the x's would cancel out and we would still get 1 to 2. Okay, there you go. Hope that helped give you an idea how to solve this problem. I'm going to end the video.